Number 74. Use the bond energy to calculate an approximate value of delta H for the following reaction, and then which is the more stable form of FNO2? Okay, so let's tackle that approximate value of delta H. Now, delta H, anytime that you see this triangle sign, that just means the change, right? So the change in the H value, and the H value is enthalpy. So we're looking for, basically, as we go from the left to the right, are we losing heat energy or are we gaining heat energy? Because remember, enthalpy, H is all around. There's an H in enthalpy, there's the capital H, and just know that this is all about the heat energy. So whether this is going to be exothermic or endothermic. Now, we want to find an approximate value, which means that we're not using the state values in the back of a textbook, but we are using the bond energies. And thank you so much, because this drawing that they gave us already shows us all the bonds. I see that I have a double bond between the O and the N, a single bond between an N and an F, and then a single bond between the N and the O. And then on this side, we see that there's a single bond with an O and the F, a single between an N and an O, and a double between the O and the N. Now, when we're using bond energies to find a approximate value for enthalpy, all you have to do is just see what is different, because that's what's changing. So, for example, I'm going to see, okay, I have an O double bonded N here. Do I have the O double bonded N on the right side? The answer is yes. Here it is. Since I have one on the left and one on the right, there was nothing about breaking this bond, and there was nothing about forming this bond, because it's been there all along. We only want to care about differences. The same thing with the N single bond O. Well, here it is. So, we didn't form this bond, we didn't break this bond, so we don't care about it. But then I look at the F single bond N, or the N single bond F, and here's the N, but there's no bond, no bond to an F. So that means that this bond, since it was on the reactant side, this had to have broke, because it's not here anymore. So this amount of energy that is required to break that bond, that's super important. And that's why we have to go to the bond energies, which I labeled as BE, to find out how much energy is required to sever or cut off that N single bond F. So in this case, this is equated to 270 kilojoules per mole. So I need 270 kilojoules per 1 mole of this bond in order to break it. Now, is there any other bond that's different? Well, on the product side, I see that I have a new bond. I have an O single bond to an F, which is not on the reactant side. So this had to have been formed. So let's just say that the 270 was broken, and this one, whatever this number is going to be, that's a bond that was formed. So just know that whenever you break a bond, that's always the reactant side, and whatever you form on the product side, that's, obviously on the product. So I had to go get that bond energy. O single bond to F is about 160 kilojoules per mole. But now what are we going to do with these values to find out the approximate delta H? Well, there's a formula. You know that there's a formula, right? The formula is this. Now it's the enthalpy change, the delta H. Notice how there's no notch up top here because we're not dealing with the state values, the actual standard values in the back of a textbook. And the delta H for this reaction is the sum, that's this symbol. So we're just going to add up, if we need to, sum of all the bond energies, BE, bond energies of the bonds broken, minus the sum, so add them up if we need to, all the bond energies of the bonds being formed. So remember, the bonds broken is the reactant side. The bonds formed is the product side. Now, in here, we just have a 270. We only have one of these bonds, and a 160 we have, an OF bond. So we don't have to add anything up. Let's just plug it in. Delta H for that whole reaction equals 270. We're going to minus it by the 160. Okay. I'm just going to plug it in because I love Calci. 270 minus 160. Calci's got to get its exercise today. Okay, there you go. Thank you so much, Calci. 110. And the unit is kilojoules per mole. So as we went from this to this was endothermic because the delta H is a positive value. Cool. Okay. Now let's just find which is the more stable form of FNO2. Now, is it this form or is it this form? Now, don't be mistaken that you can just get the formal charges to find out which one is the more stable form. Now, that will only be the case maybe, 8 out of 10 times, right? Now, if we did do the formal charges, we would see that on this one, that this has a positive nitrogen and this oxygen is negative, as opposed to this equation, or this Lewis structure, where there is no charges here. Now, generally speaking, is that the least amount of charges is the most stable. However, when you're really dealing with that type of trend and that type of rule, it usually is used for organic molecules, aka molecules that are carbon and hydrogen based. So use that just very carefully. But we can always figure out which one is the more stable form by looking at either the delta H of the reaction when we went from one form to another, or we could look at the specific bond energies. Now just know that if you have a high bond energy, right, a high amount of kilojoules that is required to break this bond, that means that you're pretty strong, right? The higher the amount of energy that is required, basically just means the higher bond energy, it's harder to do. It's really, really hard to break that bond. So if you have a high amount of energy, a high bond energy, that means that that bond is particularly strong. And if you have strong bonds in your molecule, strong bonds means more stable. So there's one way to figure out which form is more stable. Since this has a 270 versus this bond that's only 160, this has a higher bond energy. And because of that, that means that the NF bond is actually more strong or stronger than the OF bond. And if this bond is stronger, and if this bond is weaker, the more stable form would be the one on the left, even though it's got the charges. So we'll say more stable. Now, you could also figure this out by just looking at the delta H that was made. Now, in this case, we found out that the delta H was a positive value. After I'm done coloring, right, the delta H was a positive value. And this means that this reaction was endothermic. Now, in terms of stability and the more favorable type of enthalpy, just know that an exothermic reaction is favorable. So we're looking for negative values for delta H. This is always the more stable, or we'll say the favorable reaction. So as far as stability wise, endothermic reactions are favorable. But this one's got a positive, which means that when I went from this molecule to this one, not good. You absorbed energy, which means that you went from a more stable molecule to a less stable molecule. It is not favorable. In chemistry, especially organic chemistry, you always want to produce a compound that is more stable than what you started with. So that's just another reason to say that the starting material, this form, is the more stable one. And that is the final answer. What'd you think? I hope this helped you out. Please let me know in the comments. What'd you think? Thank you for tuning in, and I hope you're having a great day out there. Keep studying hard, and I will talk to you in later lessons. Okay. All right, have a great day. I'll talk to you soon. Bye-bye.